Hello, everyone. Welcome to This Week on Mars. My name is Ian Hewitt. I'm with Gupta College of Science here at Coastal Carolina University. This is our weekly podcast on things happening on Mars, especially with respect to the Perseverance rover. I say weekly podcast, but I apologize. It's been 2 weeks since we posted our video. There were some unavoidable problems, but let me assure you that Mars is still certainly there. Perseverance is still certainly there doing its job, and everything is fine with just problems on our end. Okay, this week, what we're going to talk about is we're going to talk about something really exciting, a technology demonstrator that's with Perseverance, and it's basically a helicopter drone on Mars. But I say helicopter sort of drone. Why is it sort of like a helicopter drone? Well, it's very has a lot in common with the drones that you could get, you can buy to fly around your house, take pictures of your roof, take pictures of your neighborhood. But it has to work on Mars, so there's some changes that are needed there. But also, it has to be controlled a little bit differently because of some unique factors for working on Mars. We'll talk about that. This is actually part one of the video talking about it. We're going to talk about the concept behind the helicopter and how it's implemented and some of the things. And then in the second part of the video, it will talk about its initial test and its initial flight, which has not happened as of the time we're recording this video yet. But as soon as it does, we'll record the second part of the video and cover the really exciting stuff about the test. So, helicopter drone on Mars. This is what it looks like. It's like I said, it's a small technology demonstrator. Notice right away it has two counter-rotating blades, much like a helicopter. You notice this nice flat spot on top that you may see here. This is actually a solar panel, so it can actually recharge itself. And you may see a little antenna here. The antenna, of course, is so it can communicate back to the rover. It actually uses the Zigbee protocol. What is the Zigbee protocol? If you've never heard of that, well, it's one of the protocols that's developed for the Internet of Things. So if you buy one of these smart light bulbs or smart switches or smart doorbells that talk back to a home automation hub, they're going to use one of two technologies, and one of those technologies is Zigbee. So it's a nice short range communication protocol that's pretty robust and pretty widely used. So that's what's used for. Um, so flying on Mars is a bit of a challenge. It's not quite like flying on Earth here. Flying on Earth is a challenge, but we know how to do it. But one of the problems of flying on Mars is the air is very, very thin. So how thin is that? Well, Mars' atmosphere is about 6,000 times thinner than Earth, so it's very thin. So the problem is you don't have a lot of air to move around. So you have to, when you design these helicopters, they need to be really light. Weight is very, very important, right? But the rotors also have to spin very, very fast to generate the necessary lift, much faster than they would have to spin here on Earth, right? If you look at a drone here on Earth, the rotors look like they're spinning quickly, but it's nothing compared to the ones for Mars because of the thin atmosphere. Here's a quick video that'll kind of show you. This is an animation of what it would look like. You can see the solar panels on the top of the rover, the top of the helicopter drone really clearly here. Actually, this video starts, the blades are already rotating, which is why we can't see them. And we'll go ahead and we'll start this video and just look at it really quickly. And you can see the blades out here. You can see the blades rotating and kicking up dust, which certainly we expect to do. Our first test will be just to fly it straight up and then land it. And notice it'd be doing this very close to Perseverance. Perseverance will be watching very carefully. You may have noticed there's a camera on the bottom. And then we'll actually start flying it around. It'll always stay within sight of Perseverance so that we can look at it and see what happens and how it will behave, because this is a technology demonstrator and we do want to actually test out the technology. So just a little bit about this. Um, again, looking at this, so you can see the foil box here is the warm electronics box. That's what they call that, because the actual electronics need to be kept fairly warm because they don't operate at some of the low temperatures of Mars. It uses a Qualcomm 801 processor. What is that? Well, that's basically a processor that's very similar to, like, if you ever had a Samsung Galaxy S5 smartphone. That's pretty much the technology that's in there. It runs the Linux operating system, so it actually runs an open source operating system. It's solar powered. And so those panels on top will actually charge a small lithium battery. So it won't. This particular model doesn't fly very long because the batteries aren't very big because they need to be light. But what it will do is it over the course of a day or two, it will charge up enough to fly. And it has those twin high-speed rotors that will actually do the flying. So I mentioned that it was that it was a sort of drone. Why is it a sort of drone? Well, the reason it's a sort of drone is because light speed, right? So light speed is not really a factor here on Earth because it's really fast. It's really fast, but it's finite. It's not infinite, right? So like here on Earth, light speed isn't a factor, right? For example, in speed limit, 186,000 miles per second. We say it's not just a good idea, it's the law, it's physical law of the universe. And what does that mean? Well, that really means that you could, in a second, you could go around the Earth 7 times a beam of light. So pretty much when you're here on Earth, light speed's not a factor. So when you're using, uh, so when you're actually using your controller to control something, whether it's a drone or a video game, uh, you can do that because the delay, the small delay of time it takes light to actually travel to the game, and for something to happen and for you to see what's happening is so small. It's basically like that. So that's why a remote control drone here on Earth will just respond instantly to your commands, and you can kind of see what's happening. And if you're headed towards something, you can turn it around, stop it, or even land it or anything like that. So where that starts having and where that starts having trouble is when you get farther out. For example, if you were to do a drone on the moon, could you do a drone on the moon and just sit there with a controller like this and control it? Well, probably if you were good, because light speed starts to come into a little bit of play with the moon. And this is just going to be a little animation. And you see the little beam going back and forth. So you can see there's a little bit of a delay here. Not much, you can see that you would if you go ahead and make a control and all of a sudden you see it, make control, see it. That's not a very big delay, right? You could do it. Now you'd have to like anticipate what's happening. It's like it'd be like using a really slow game or a game on a really old computer that doesn't have enough processing power. It's a little bit slow and you kind of have to anticipate it. But it's not too bad. The problem is when you get to Mars. And when you get to Mars, this is a little bit different. The technology is going to be different, and the problem is the time it takes is going to be a lot different. So my animation here is seeming to have a little bit of problem. But there we go. So when you look at Mars, and this is the best case when Mars is closest, and you can see you just launched a light beam. And speed of light in real time, one way is 3 minutes at the closest approach on Mars is. And I'm still talking here for 3 minutes, so you basically have like made a control motion, and we're still waiting for it to go. 3 minutes doesn't sound like a lot of time, but it really is when you're trying to control something in real time. Imagine if you're playing a game and you go ahead and make a control, and it still hasn't to move a direction, and it still hasn't gotten there yet. You see, we're still going, and that's the one-way light time. And make it even worse, this is the best case. When Mars is farthest from Earth, it's a 20-minute light time. So the fact is, it's still going, it's still going, it's still going. And you can see this is how long it takes for signals to go back and forth. So think about it this way: if you were actually trying to remote control that helicopter on Mars, then it would be a case of you might see it coming up on a mountain, right? But for you to see that, it sends you the picture of the mountain. It takes 3 minutes. Again, we still haven't gotten what you to get that information. And then it takes 3 minutes. Then you can say, okay, well, turn. It takes 3 minutes to do that. So you actually would have to be like 6 minutes ahead. Or in the case when Mars is far away, you'd have to be 40 minutes ahead. And that's really hard to do. So you can't really control things in real time. That's why both the Perseverance rover and the Mars helicopter Scout are like drones in that they'll take commands from Earth, but they have enough intelligence on board that they will basically be able to manage their own flight. The drone has to be able to figure out if it's going to crash into something to either go around it, stop, go back, figure that out on its own. That's why it has those cameras on the bottom. It's got several cameras actually, so they can look for obstacles, and if there's a problem, avoid them without having controllers tell it to do that, because we really can't do it. So you can see, even in all this time that I've been talking, the speed of light, the one-way time, has not elapsed. So it really gives you an idea about why you can't actually just do like the remote control thing on Mars, right? Now, so why do we do this? Well, that's a good question. The thing is, when we send human missions to Mars, you're going to want the ability to explore wide expanses of Mars, and that having like a helicopter drone ship would be a really good idea. You also may want to go somewhere that's really dangerous, like down in a valley, or somewhere like that, or down in a cave. And again, it's a lot easier to use helicopter drones. Once we have humans on Mars, of course, then you can actually control it in real time because you're actually very close to it. Now you see we're actually finally the signal is getting back here to Mars, and then it will turn around and start coming back. So you can see just how long that 3 minutes really is. So what you would see is here's how basically what will happen, or what did happen on Mars for deploying the helicopter. Now this is actually in the lab, or in the assembly room, right, for all the testing. So I'll show you the pictures from Mars, but here this kind of shows you a pretty good view of what actually will happen. So the first thing is the helicopter was stashed up under the rover behind a debris shield, behind like a big cup. So the first thing that will happen is we'll actually, let me go ahead and fire off this video. And it drops that debris shield, right? And then you actually see the helicopter itself. Then it will unlock, as you just saw. And then it will flip down, and flip down slowly, because you don't want to break anything, because you can't really call service on Mars. And then what it will do is you see the legs drop, and then very quickly it'll actually drop to the surface of Mars. And then the trick is the rover will drive away, and this will keep, and then the helicopter will be on Mars, right? So when we look at it in person, here's some actual pictures from on Mars, that using the camera on the front of the rover on the arm, so it can kind of look up underneath itself, and it will actually, this is the actual drop of the pan, and then Ingenuity will drive a little bit forward because you don't want to stick the helicopter back in the pan, and then this is kind of an animation of images. These are actually real images on Mars. It drops it and has put it down on Mars. We'll look at it again, and you can see the legs drop. It will drop it, and you don't get a picture every time because they were taking just pictures at certain intervals. But it is actually out on Mars, and the rover is not on top of it anymore. So that's actually a really good thing. Here's actually one of the first tests they did right after they dropped it while the rover was still over it. They actually fired up the cameras on Ingenuity, and here's actually a picture from Ingenuity. So we know that communication with Ingenuity works, and we know we can talk to it. So for next time, we'll talk about part 2 of the video. Some of the things that are already happening as we're making this video is you need to unlock the rotors. They will do a rotor spin test, a high-speed rotor spin test, to make sure they rotate. And the first test flight, that's the one where you go up and down, and then followed by some additional test flights. So we're looking forward to that, and we'll actually talk more about that either next week or the week after, depending on when they complete some of these test flights. Well, that's it for this week. Thanks for listening, everybody. Have a great week.